For today's vocabulary video, you will need in class 25, which is part of standard number 6. This is actually our first day learning about angles that are formed when lines are cut by a transversal. So we're going to start by figuring out what a transversal is. That's actually the dark, bold line in this top picture. And so the idea of a transversal is that it's going to be a line that intersects two or more other lines. So I'm going to highlight our transversal yellow just to make it pop out a little bit. And then what makes it a transversal is that it's intersecting two, in this case, other lines, but it could also be more than two other lines. So it is transversing, it is passing through two or more other lines. When that happens, there are 8 angles formed when there are 2 lines that are passed through. If there was a third line that it passed through, then there'd be 12 angles that are formed. And these angles have different names and then different relationships that we will see depending on the properties of these lines that are intersected. And so we're going to learn what the names of those angles are, as well as what is true about those angles in certain scenarios. And so as we get started, we are going to look at different angle pairs that have been bolded in these 4 diagrams. And so if we're looking at an angle pair that looks like this, we're really focusing in on this angle and that angle. And so there are a couple of characteristics that you want to pay attention to know whether or not an angle pair fits this particular type of scenario. These angles are what we call angles on the same side of the transversal. If we highlight that transversal yellow, just like before, those angles are both kind of above, or maybe you think about it as to the left of that transversal. And that's going to be the case for the angles that are directly below that as well. These angles, so this one and that one, are on the same side of this yellow now transversal. So the 2 types of angles we'll cover on the left side of your notes are angles that are on the same side of the transversal. The alternative to that is that the angles are not on the same side of the transversal. If I highlight the transversal in this picture or in this picture, the angles that we're focusing in on right here and here are on what we call alternate or opposite sides of that transversal. This one would be above the yellow line, that one is below. Same thing here. This one is above that yellow line, this one is below. And so we call those angles that are on alternate sides of the transversal. They alternate versus being on the same side. So then the second characteristic we need to look at is about their location in terms of the lines that are transversed, the other 2. So if we look at this top right corner to begin with, here are 2 lines that are intersected by our transversal. When we highlight those 2 pink, do you notice how both of these angles get trapped between those lines? This is what we call the interior space for this picture. And so these angles are both alternate because they're on opposite sides of the transversal, but they are interior because they're in between those other 2 lines. That gives us the name alternate interior angles to go with that kind of a relationship. So if we pop back up to our original diagram and we're trying to list some possible pairs of alternate interior angles, we would want to make sure that we're sticking with angles that are in this interior space. Okay, so our options are going to be 6, 5, 3, and 4. So if I start with angle 6, that's up here on this pink highlighted line. I need to follow my transversal down, but then go to the alternate side. So angle 6 and angle 4 would be an example of alternate interior angles. There is a second option. If I start up here, angle 5, travel down the transversal on the alternate side would be angle 3. So angle 5 and angle 3 are also an example of alternate interior angles. If we look at what's happening in this diagram, directly below our alternate interior angles, we still have these two lines that are being intersected by our yellow transversal. This is still what we call the interior space. And so you'll notice in this one, both of these angles are outside. They're not interior. So we're going to call these alternate still, based on how they interact with that transversal, but they are going to be called alternate exterior instead of alternate interior angles. So if we're looking at alternate exterior angles in this diagram up top, we're going to avoid all the ones that are in that interior in-between space. So maybe I'll start with angle 8. I would need to look at angle 8, slide up the transversal, but go on the other side on the exterior. So angle 8 and angle 2 would work as a pair of alternate exteriors. Or angle 7, slide up that transversal, go all the way to the exterior on the opposite side, would give me angle 1 to pair up with angle 7 to make alternate exteriors. So those are the two types of angles that you're responsible for when we are dealing with alternate sides of the transversal. If we slide back over to the other side, when we're dealing with angles that are on the same side of the transversal, these are both in the interior of that system, right? If we highlight those lines that are intersected by the transversal, both of those angles are trapped there on the inside in that interior space. But they're not alternate. They're on the same side of that transversal. So these are what we're going to call consecutive. That means that they're right in a row. Interior angles. So if we look here, we've got an opportunity to use the picture at the top to name some consecutive interior angles. I'm going to go to my picture, focus on the interior space. So 3, 4, 5, and 6 are my options. If I start with angle 6, I need to stay on the same side of this transversal. So that would get paired up with angle 3 to be consecutive interiors. Or if I'm looking at angle 4, another interior angle, stay on the same side of the transversal, it would get paired up with angle 5. The final type of angle is a little bit different than the others. In all of the others, the angles have either been both interior or both exterior. And if we're looking at the angles in this picture, if I make that interior space pink, one of my angles is in there, but the other one is not. So this type of angle has one interior angle and one exterior angle and stays on the same side of that transversal. We call these corresponding angles. And the reason they're called that is because if I check out this little group of 4 angles here, this angle is below the pink line but above the yellow. If I go check out this group, same thing. This angle is below the pink but above the yellow. So they're in what we call corresponding locations. So when we look at our picture over here, there are more sets of corresponding angles than there are any of the others. Let's say I start with angle 8 because that looks like this angle out here. Angle 8 would correspond to slide up your transversal but stay on the inside since 8 is outside. So angle 6 and 8 would be a set of corresponding angles. Or let's say I hop over to this side of the transversal on the outside. Angle 7 and angle slide up but stay inside. 5 would be a second set of corresponding angles. Or let's say I start out on the interior. So angle 3. That means I'm going to slide up that transversal, stay on the same side, but move it to the exterior. So angle 3 and angle 1 would be a third set. And then last but not least, if I started off with angle 4 on the inside, slide up the same side of that transversal, but find the angle on the outside, angle 4 and angle 2 would be your final set of corresponding angles. All right, that's the vocabulary on the front side of the page. So we're going to slide down to the bottom of that and do some examples. And you'll notice that things get a little more complicated down here because there are actually 4 lines drawn in this picture instead of the 3 that we've been focusing on. And so what that means is that any of these lines, K or L or N or M, could be acting as the transversal because they all intersect 2 other lines. So what we're going to do is we're going to focus on identifying the transversal first, and then we're going to try to give a name for the type of angle they are telling us to focus in on. So the way to do that is to start by finding these 2 angles, angle 14 and angle 16. The transversal is going to be what connects them. So I'm going to go ahead and highlight from 16 to 14. That is going to be the transversal. So we're going to name that line L. So when we're investigating line L, we can see that 14 and 16 are both below the line. So they're on the same side of the transversal, which means our choices are either that they're corresponding if one's interior and one's exterior, or they're consecutive interiors if both are interior. So if I'm looking at these other lines, it looks like 14 is trapped in that interior space, but 16 is not. This is like the bottom left out of that little group, and so is 16, bottom left. These would be an example of corresponding angles. Moving to the second example, we need to find angle 12 and angle 7. So that means we have a new transversal. To connect angle 12 to angle 7, I'm going to have to travel line M. So I'm thinking about that pink line now as being my transversal. So when I look at that pink line, 12 is to the right, but 7 is to the left. So I am in alternate mode. So I need to make a decision between whether both are exterior or both are interior. So when you're looking at these 2 angles, we're going to transfer to the other lines that are intersected. Looks like 12 and 7 are both trapped between those lines. So they are interior angles. Alternate, but then interior. Alternate, interior angles. If you'd like, you can pause and try to answer these next 3 on your own and then come back and see how you did. Or if you're not feeling ready for that yet, then just keep on watching. Angle 2 and angle 7 are up next. So I'm going to find them. Angle 2 and angle 7 are up here. I'm going to grab a third color, hopefully here. The line that connects them is going to be the transversal. So that looks like line K this time for a transversal. 2 and 7. 2 is above, 7 is below. They're on alternate sides of that transversal. And if I look at the other 2 lines, they're still trapped in that interior space between those other 2 intersected lines. So this is a second example, just like 12 and 7, of alternate interior angles. We're just using a different transversal this time. On we go to angle 1 and angle 8. So if I find angle 1 and angle 8, they are also connected by line K. So we're going to stick with the same transversal. But if I'm looking at 1 and 8, 1 is above and 8 is below. But if I imagine this interior between space being highlighted, they are both exterior angles. So this will be our first example in this little section of a pair of alternate exterior angles. All right, last but not least, we're going to look at angle 12 and angle 8. So 12 and 8 are over here. They are connected by that pink transversal we used earlier, which is line M. Looks to me like they're both to the right side of line M, the transversal, so they're on the same side. If I look at these other two lines, they would both be in that interior space. So that is an example of our fourth and final type of angle. Those are those consecutive interior angles. Same side of the transversal and both in the interior space. All right, let's go ahead and flip the page and see what else happens. We are going to now change gears a little bit. So we're introducing a new idea on this side of the notes, and that is what happens when lines are parallel to each other. Parallel means that they are never going to intersect. So they never get closer together, they never get farther apart. And so what we need to investigate is what happens to our four types of angles in that particular scenario. We didn't have that on the front side because we were just dealing with random lines that had transversals. So now we're being a little bit more specific with what we're dealing with. Okay, the first thing we're going to look at is corresponding angles. And we're going to go through kind of like a proof or justification process. It's going to seem a little bit weird for this one because it's not going to be written in two-column format. But what we're going to think about is what happens if points A, B, and C are translated. So think back in your mind to what it looks like for things to be translated, back from standard 4. And the way that we're going to do that is we're going to translate directly down the transversal. So we're going to move all three of these points, because we're focusing on this angle right here, we're going to translate them down the transversal the same amount. I'm not going to measure with a ruler, I'm just going to kind of eyeball it. But what's going to happen is that A is going to slide a particular amount and become A prime, okay? B is going to slide that same amount and become B prime. And then last but not least, C is going to slide that same amount and become C prime. And so what happens if I do that, I'm translating A, I'm translating B, I'm translating C. If I reconnect B prime and C prime to each other, try to do this carefully so that it looks like it's supposed to look, I end up getting a new line here through B prime and C prime. Sorry, that sketching is kind of terrible. B prime and C prime. And I end up getting a new angle here as well with my A prime, my B prime, and my C prime. But we know a couple of things happen when we translate. The first thing that happens, even though we didn't talk about this back in Standard 4, is that this line that we just created ends up being parallel to the original line that we started with. The way that we show that in a diagram is by putting a little flag on the line, kind of like a tick mark, but it looks like a little arrow. So you can put a single or a double or a triple, just like with tick marks. And then the other thing that happens is if we think back, translations, remember, are rigid motion. And so that means that our angle measure is not going to change. So what we have right here and right here are corresponding angles because they're on the same side of that transversal. One's exterior and one's interior. And those corresponding angles have to end up being congruent because they happened as the result of a translation. And so what we end up with is actually a postulate that we're going to talk about. It's called the corresponding angles postulate, if you want to add that in here just so that you remember that it's called a postulate. And that is that corresponding angles will always be congruent if we have parallel lines. So anytime we see our parallel lines, we're going to know that those corresponding angles are identical in measure. If one of them is 100 degrees, the other one is also 100 degrees. Okay? Now, building off of that idea, we're going to look at alternate interior angles. Okay? This idea is going to be a theorem instead of a postulate, if you want to mark that out so that you're aware. And so what's going to happen is we're going to start with our parallel lines. That is what we see right here with these flags. And so basically what we're given in our picture is a fact that line K is parallel to line M. There is a symbol for parallel. It's two vertical bars that look parallel. And so instead of writing that out in English, we can write line K is parallel to line M. So that would be our first statement that we're given based on how this diagram has been drawn. Now there's not a whole lot we know about parallel lines except what we just figured out up top with a translation. We know corresponding angles are going to be congruent. So in this picture, we actually have a couple corresponding angles called out. We've got angle 1 and angle 2 that are on the same side of this transversal. 1 is exterior and 2 is interior. And so we would be able to say angle 1 is congruent to angle 2 thanks to what we just talked about above, that corresponding angles postulate that we just worked through with our translation knowledge. So that's a new reason that we haven't seen in a proof before, but we now know it. Now there's something else we can say about this diagram based all the way back in Standard 2. Take a look at angle 1 and 3. Think about what you know about those. I am hopeful that angle 1 congruent to angle 3 is what came to mind, because those angles are vertical angles, and we can keep on using our vertical angles theorem that we learned a while ago. All right, our goal in this proof, if we weren't clear from the beginning, was to get to some kind of information about alternate interior angles. So when you're looking at this picture, we want angles that are on alternate sides of the transversal, but both in that interior space. So that means we want to talk about angle 3 and angle 2. So let's investigate. Angle 2 is the same size as angle 1. Angle 3 is the same size as angle 1. If these both match angle 1, does it make sense that they have to match each other as well? So we're able to make kind of like this logical chain here that says if angle 2 is the same size and shape as angle 1 and angle 3 is the same size and shape as angle 1, we can cut out that middleman, that angle 1, and just say that angle 2 and angle 3 are the same size and shape. That is a new reason called the transitive property that we will use when we are dealing with parallel lines. And sometimes it's nice when you're using the transitive property to show which two lines of your proof you're combining together. So I combined line 2 and line 3 together, and that's where this new line 4 came from. So what we started with was parallel lines. We used our corresponding angles and our vertical angles, and what we ended with was alternate interior angles that are congruent. And so what we've proven is a new theorem. Alternate interior angles are congruent anytime our lines are parallel. So we've covered corresponding angles, we've covered alternate interior angles. We're going to take a look at consecutive interior angles next. Consecutive interior angles are a little bit different. So let's think about this picture. We're not going to write this in a formal proof. We're just going to think about it. Angle 1 and angle 2 are the ones they want us to focus on first. Looks like I have an angle symbol missing. So if your copy has one missing, go ahead and add that in there. Those are on the same side of the transversal. And angle 1 is interior. Angle 2 is exterior. So those are going to be corresponding angles. So if we know, like they're saying up here, that the lines are parallel, we're going to add some flags to those lines to show that. Up top, we talked about how corresponding angles will always end up being congruent. So I would be able to mark that angle 1 is congruent to angle 2, as long as we know that these lines are parallel. Taking a look at angle 3 and angle 2, angle 1's not even in the mix anymore, so I'm going to cover that up. We've got back-to-back angles that are making a nice straight line right here. Take your brain back to standard 2. What's it called when angles are back-to-back like that, making a nice straight line? I'm hopeful that you're coming up with the phrase linear pair. Linear pair angles are not congruent. They add up to be 180 degrees. So let's think about that. If I have the measure of angle 3 plus the measure of angle 2 equal to 180, that's my linear pair fact. And I know that angle 1 and angle 2 are the same size. I could take this angle 2 out of there and I could make it an angle 1, substitute it in basically, because these match, so they have to be identical. And now all of a sudden I have a fact about my consecutive interior angles. They are not equal to each other. They take a sum in order to be combined to make up 180. So we've got the measure of angle 1 and the measure of angle 3 combining together to make 180 degrees. The word that we used for that back in standard 2 was supplementary, because they're not a linear pair. They're like facing each other instead of being back to back. But they do add to 180, so we can use that supplementary vocabulary word. Okay, so we have figured out when lines are parallel, corresponding angles are congruent, alternate interior angles are congruent, consecutive interior angles are supplementary. This one is also going to be a theorem if you want to add that in there. So the only type of angle we are missing out on, if you flip the page, is alternate exteriors. So let's try to figure out what's happening with these before we're done with our vocabulary part and we can move on to our examples. We are starting again with lines being parallel, so I'm going to add that onto my picture, which means the only fact we really know at the beginning of this is that line K is parallel to line M. So if we are focusing in on angles, I'm thinking the best place to start, like we did before, would be with angle 1 and angle 2. Those are on the same side of the transversal. Angle 1 is interior between K and M. Angle 2 is exterior. So those, again, are going to be congruent because they are our corresponding angles. And if those lines are parallel, we can use the corresponding angles postulate to show that angle 1 is congruent to angle 2. Then it looks like, again, I have some vertical angles in the picture. So I can show angle 1 is congruent to angle 3 using that vertical angles theorem. Very similar to what we did earlier with our alternate interior angles. But this time, if angle 2 is congruent to angle 1 and angle 3 is congruent to angle 1, I can repeat that whole transitive property thing that we talked about, and I can make angle 2 congruent to angle 3. So this should feel very similar to before. I'm combining these two statements together with the transitive property to make angle 2 congruent to angle 3, but this time, take a look where they're at. They are on alternate sides of that transversal, but they are not interior this time. They're exterior angles. So I have figured out through this little proof that alternate exterior angles are also congruent when lines are parallel, which rounds out your last fact about what happens when parallel lines are cut by a transversal. And this one is also a theorem. All right, the rest of what we have to accomplish is just practicing using that information. So if you want to pause and try to practice on your own and then come back and check it, that would be absolutely fine. We're going to go into this first set of examples. And right away, I notice we've got these flags. So that tells me that these lines are parallel, which means I get to use all of these new facts we've just proven are true. And this line right here is going to be the transversal that passes through those lines. So let's take a look. If angle 7 is 100, so this angle down here is 100. Angle 3 is the request. Same side of the transversal. 7 is exterior, 3 is interior. So I actually start by figuring out what kind of angle they are. They are corresponding. And then I think back to what's true when lines are parallel. Corresponding angles are congruent. So that tells me that this angle's measure will match and be 100 degrees. Next up is angle 1 and angle 7. So 1 and 7 are on alternate sides of the transversal, which means that's going to be part of the name. Neither one of them is between the pink parallel lines. They are on the exterior, so that finishes out the name. Alternate exterior angles are what we just talked about directly above. They are also congruent, so that means their measures will be the same, 120 degrees for both. Angle 3 and angle 5 are up next. So here's angle 3 and 5. I notice they are alternate as well, but this time they are interior. So if we think back to when we learned about alternate interior angles on the last page, they were congruent as well. So their measures will both be 140 degrees. Now before you think this is smooth sailing and everything's just always going to match, remember we have one type of angle, angle 3 and angle 6, that are on the same side of that transversal but are both interiors. We called those consecutive interiors, and those angles are not equal. These are the angles that are supposed to add to be 180 degrees. So when we are given consecutive interior angles, if you just grab that 125 and call it good, you're going to get yourself in trouble. Instead, we need to make sure that we make them add up to be 180 degrees instead. So measure of angle 6 will actually be 55 degrees. All right, one more set of examples before we're done. Again, if you want to try it on your own, go ahead and pause it and then come back and check your answers. First up, we're going to have angle 7 and angle 12. So 7 and 12 are over here, connected by transversal M. They are on alternate sides of that, but interior when it comes to those parallel lines. So alternate interior angles. Since these lines here have those flags, we know that they're parallel, so we get to use our new theorem that tells us that those angle measures will be the same. They are congruent. 1 and 9 are up next. They're connected by a different transversal over here, but it's still intersecting those parallel lines. They are on the same side of the transversal. 9 is interior and 1 is exterior, which makes them our corresponding angles. But again, corresponding angles are congruent, so 125 degrees. Next up is angle 9 and angle 5. Transversal is N. They're on the same side, but both are interior. Ooh, those are our consecutive interiors, which are the ones that are different than all the others. So that means that these angles are not congruent. They need to add up to be 180 degrees. So we need angle 5's measure to be 40 to make that happen. And then last but not least, angle 3 and angle 13 use transversal M. They're on alternate sides of that, but neither of them is between the parallels. So they are alternate exteriors, and alternate exterior angles are congruent. So if angle 3 is 91, so is the measure of angle 13. All right, that is it for in class 25. We'll see you back in class.